Oh, JP, in your next video, put 4 problems in it. That's ridiculous. How am I supposed to put 4 problems in it?
JP, I got 4 problems.
Oh, you did?
Yeah.
Where'd you even get these 4 problems?
I don't know.
Yay! Wait, doesn't that mean that's gonna be totally convenient from the... Oh, we're recording. Gimme. Keep that out. Hello everybody, this is Great Math number 81 with me, JP, and today I have to do 4 problems with you guys. I know it's probably gonna be pretty hard. Wait, no, these problems aren't that hard. These are gonna be lightning quick ones, okay? So this is in the chapter of probability, in the book of probability and counting. So what we're going to do here, we're going to do a probability of how many words we can mix up, kind of. So here, let me give you an example. Okay, sorry whoever put this note. Actually, I want to use red. Okay, so for the first one, how many distinct arrangements are there of the letters in the word dog? Okay, so in the word dog, we don't really want to see, as you can see in this one, how many distinct letters how many possible distinct arrangements are there in letters in the word dog. Now up here, we know that they don't necessarily have to make sense. Like, it could be any scramble. Now, some of you guys will see, okay, so there's this arrangement, and there's this arrangement. No, I don't want you guys to do that. There's a lot smarter way to do that. Instead of just doing this, doing that, we will actually use some factorials to this. Now you guys will be saying, how does factorials have to do anything with this? Well, I'll show you right now. In the word dog, I'll show you. So, we know there's 3 letters, right? Okay, so we'll make 3 slots. Now, each letter can go in any slot. So let's say, okay, the letter D goes here. So that meant before that there were only 3 chances. Now because that's taken, there's only 2 chances left. So we pick O. And because of that, there's only 1 chance left, and then there's the letter G. Now this can go in any order, but this is why I want it, because there are slots here. Because of that, then you multiply, and like I said, counting and probability, this isn't necessarily or, it's and, because you have to combine them to make the total amount of possibilities. It's not going to be this amount of possibilities or this amount of possibilities. No, it's going to be all of them combined. So 3 times 2 times 1, which when we bring up together, it's actually 3 factorial, like we said, or if we want it in simpler terms, it's basically 6. So there are 6 total possibilities or arrangements to mix up the word dog. Okay? Okay, number 1's out of the way. Now we're down to problem number 2. How many possible distinct arrangements are there of the letters in the word ball? Okay. So, the word ball. Oh. Okay, it's singular. Okay, so now you would think, okay, we can think of 4 slots now. 1, 2, 3, 4. That doesn't necessarily make it what we want. Now, because there are 2 letters that are exactly the same, that kind of makes it complicated. Now so that means this is only 1. You guys could actually, let's say that's L1 and it's L2. You could say that this is another arrangement. But in this case, because they're so identical, they are not at all. Actually, because I don't think I'm going to use this word. Just a second. Last minute stuff. Okay. You would think that would be fine, but that's not really what we're looking for here. But for now, we actually will do that. Like, we'll pretend L1 and L2 are different, that they are totally different numbers. So because of that, we make the 4 slots. and we make slot 1, say B. 4 chances left. Now we only have 3 chances left. Then 2, then 1. And then this all makes 4 factorial, which is equal to 24. But we are not quite done. Let's keep 24 in our minds, okay? Now we have to account for... Now, that would be way too much, because in real life, these two are identical. Meaning it's totally different. So basically we would be overcounting. And there's a lot of problems that you overcount, which is bad.
Can you give an example of overcounting? For example,
Okay.
give me 2 combinations where you overcount.
Let's take the word ill. Let's say I'm very ill. I'm ill. Okay, so L1, there's L, 2 L's. Now really, how many possibilities are there here? It's easy, there's 1. This one we can actually count. There's 1, if we put the I here, and it's 2 if you put the I in the middle, and 3 if you put the I here. Making the L's fill up the places that it's not in. So we know there's actually 3 possibilities. Now because we see, oh okay, there's 3 letters, make 3 slots, 1, 2, 3. There's an I, 1, that's 3, another L, 2, and 1 last L, it's 1. That is 3 factorial, which is 6, which is just 6. Wrong. Nope. It is not. That is an example of overcounting. Now we don't want to overcount, we want to get this problem right.
No, you overcount because
We overcount
if you name
because
L1, L2
yeah,
equal L2, L1. Is that right?
Yeah.
Okay, explain to me.
Basically, we don't want to overcount the L's because they're identical. It doesn't matter. So if we did this and we switched the L's, that is the exact same word. Ball is still ball, right? So we want to count in a different way. We see there are 2 L's. Now, we can make a whole line of L1 always being in front of L2, no matter what scramble. And we can make another line that L2 is always in front of L1, no matter what. So, because of that, we need to find the... Now, because of that, we need to find this. We know that there's a we need to find basically, sorry, wrong equation. There are 2 letters here, right? So basically we have to mix up whatever the factorial or whatever there is. So basically there are 2 of them. So basically it's 2 factorial, which is basically 2. Now, in this case, because we don't want to overcount, we have to divide. So the number was 24, right? Right? Okay, it was 24. Divide by 2. We divide by 2 because we don't want to overcount. It's accounting for the 2 when they are. It's accounting for, it's kind of like, I'm guessing it's kind of like you minus or something like that. I don't know. It's like you're taking away, because you divide it, you're taking away the possibilities of it being free, of the L's moving around, or them being different. We're taking away that possibility by dividing it. That way we know, we take away the possibilities or the overcounting, because we know these are identical. So we're changing that, and we're trying to make sure that we don't get that overcount. Because that, the answer to our ball question is 12. Okay? Let's move on to the third one. How many distinct arrangements are there of tatter? Okay. Now tatter, we can see there's 3. Okay? There's 3, so that's going to be a bit difficult. Okay. Okay, we see there's 6 letters. Now this is for the top, or let's pretend it's like this. T1, T2, and T3. Okay? Now, because of that, now we know there's 6 letters, we make 6 slots. And I'm just going to do this to save time. T, now there was 6. Then there's the A, Now there was 5. And then we know there's 4 going down to times 1. So basically all of this is 6 factorial. Or, all you mathematicians and mathematicians know this, 720. Yeah. But that's way too much because we know that these are identical, like I said before. Now because there are 3, we don't divide by 3. Okay? That's why I said it was 2 factorial, if you guys were listening. I divided by 2 because, well, it is that. Basically, an easier way to do it, which I think would have been better for the last problem, it was 6 factorial, right? No, it was 4 factorial, yeah. 4 factorial divided by 2 factorial. That's a better way to think about it. Instead of just writing out the entire number 24 divided by 2 because you think you just cut it in half, but no. In other words, we don't divide by 3 here. So like we said before, we need to make the order that there's 3 of these, right? There's 3 of these. We need to make the order of every time 1's in our front, 2 is the second, and 3 is the third. And then we need to think of all the orders that if 3 is in front, 2 is in front, 1's in the back. We need to make all of those arrangements. Sorry. Yeah. Okay. So after that, we know that those 3, this including A, they are 3 factorial because there are 3 numbers, or simply known as 6. So when we write our entire equation, 6 factorial divided by 3 factorial, it's basically 720 divided by 6. Now, if you guys really want to be crafty about this, you can pause the video right now and go try to tackle that problem right now. But I already know the answer. So,
Well,
you guys pause? Okay, you guys are done finding it. And we know it's 120.
or what you can do 6 equals 6 times 5 times 4
Oh, yeah,
times
we can
3.
do what? Or, if you guys really want to avoid doing that, doing it a different way, and some of you guys who already paused probably know this way already. 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. Cancel out, cancel out, cancel out. We get 6 times 5 times 4, which is 6 times 20, which is 120 possibilities for the word arrangements, for tatter. There we go. Now, I specifically covered the last problem because I didn't want you guys to do it ahead. So I'm going to erase the board right now. Flip the page and you guys can see the problem. Come here.
Jean-Pierre.
Oh, wait, give me a second. Yeah. So you guys can see it? Yeah. How many distinct arrangements are there for of papa? Of the word papa.
Okay, go ahead.
Okay. So that means there are two pairs of identical letters. You guys can see. Right? So that's going to be a bit more confusing. Now first, like we did, we're going to do the maximum, or of course the overcounted solution. We have 4 slots. There was 4 for the letter P, and then for the next one it could be any for A. So do that. Actually, we'll just make this A2 just because some of you guys might not know that I said that it could be any, and then there can be P, but then there's only, 2 possibilities, and then there can be A1 for the last possibility, which basically that makes this 4 factorial, or better known as 24. Now you guys need to remember 4 factorial and 24, okay? Thanks. Now we need to know the wrong count, okay? So basically what we need to do, you see that we need to make and then we need to make sure that the 2 we need to go over the 2. So basically there's 2 factorial for the p. And I'm going quick here. So that means there's basically 2. And this is for the p. And it also goes for the a because there's 2 letters on that. So yeah. So then, like we said, we have 4 factorial divided by 2 factorial. But that's kind of wrong. Because we have to include the a, we have to multiply that too. Because it's and, like I said, in probability and counting. So 2 factorial times 2 factorial are the denominator of this. Now when we get that, we get 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. Cancel out. That's all what already canceled out. That cancels out. That's going to be 12 divided by 2, which is an answer of 6 for our answer. There are a total of 6 for this. And that is actually about all that we have for today. Now, I hope you guys enjoyed this video. Please do subscribe. Please punch that like button in the face. And if you would like to see more videos, please do subscribe to Great Math with me, JP. And I will see you guys next time. Goodbye.